Okay, well, let me get back. Inadvertently, you put me back on my train of thought that I was on, that I deviated.
Do I get a bonus?
We'll talk about that after class.
Cheat.
See, here's the problem with an ice age. What I was saying was you cool the climate down. You have the thing, what's the hydrological cycle? What's the hydrological cycle?
That's where you get evaporation, makes a cloud.
Water is evaporated up out of the oceans, just like Jerry said. It forms clouds. The clouds go over the land. It precipitates out, usually as rainfall or snowfall, sometimes as sleet and other things, but mainly rainfall and snowfall. If it falls in a northern climate during the winter as snowfall, it accumulates and there's a temporary interruption of the cycle until spring comes, and then it thaws, and then the cycle continues. With the onset of a glacial age, it's sort of like, imagine how the cycle is interrupted for 6 months. If you live in the northern United States, you know that once you get to about late November, early December, precipitation falls as snow, and it doesn't rain again until probably April or early May. So you've got this interruption of the hydrological cycle, right? But you know spring is going to come along, and then the snow is going to melt away, and then you're going to have warmth, right? If an ice age comes on, imagine it's the same thing, except that spring just never shows up. In fact, well, it eventually does 10,000 or 15,000 years later. But that'd be a very accurate way to think of it. Oh, so now that the snow does not melt in the spring, it just rolls right over, and the next year's accumulation of snow falls on top, and then the next year, and then the next year. And after about 3 or 4 or 5,000 years, you've got thousands of feet of glacial ice formed. But the problem with that is simply this. When you lower the temperature, you basically slow down the hydrological cycle. When you look at the onset of a glacial age, what you see is the very rapid accumulation of huge glaciers over literally millions of square miles of landmass, up to thousands of feet thick, which requires essentially it requires a hydrological cycle on steroids. But the problem is the climate's obviously cooler, or you're not going to accumulate the ice. So there's a major contradiction right there that has not been resolved. But again, the attempts to resolve that paradox have all been based upon models that are exclusively Earth-based. As soon as we began to allow our thinking to expand to the cosmic domain, we discovered that there are forces and phenomena that could achieve such an interruption of the hydrological cycle. At the same time, here's the problem. How do you simultaneously shut down, put the Earth into deep freeze, but then you accelerate the evaporation and precipitation cycle? How do you do it? Well, it's what you were suggesting, Elizabeth. You can do it by an accretionary process. You can do it by introducing materials and energies from outside the terrasphere. Now, in order to precipitation, you have to have, every raindrop has a nucleus. So in the aftermath of Tunguska, remember what happened in the aftermath of Tunguska? There were these strange rainfalls that lasted for several days. A lot of other of those type of cosmic events have been associated with rainfalls. It created this fine dust in the atmosphere, and those little particles of this cosmic dust formed nuclei around which raindrops accumulated and fell to Earth. Now, what would happen? We have to begin thinking now about the kinds of consequences of things like comets exploding in the atmosphere, comets and asteroids landing into the ocean, comets and asteroids landing onto ice sheets, comets and asteroids hitting the ground, causing fires, but maybe in some scenarios simultaneously hitting the ground and hitting a water source. If you could simultaneously hit the ground and create fires and inject lots of dust into the atmosphere, at the same time you land one in the ocean, I think you've got all the ingredients you need. You've got an enormous amount of particulate matter injected into the atmosphere, as well as huge amounts of water vapor. And if the water vapor precipitated out, the particulate matter did not precipitate out, what you would end up with is a canopy, a veiled canopy over the atmosphere that would reduce the amount of heat getting to the surface. So I think, again, that's a very rough estimate of the model, but I think that's one way you could explain it. Take a look, Sam. Here we're seeing some of the effects of the Little Ice Age. And this is from the period from about the 1850s to 1970. And you can see the difference. It's very clear. See the arrow there? And you can actually, you see the line right there on the hillside? All right. Now, most of this recession occurred before humans were having any discernible influence on the climate. And we've got lots of those. Now, see, this is an example of a Little Ice Age moraine right here. This photograph was probably taken in the 80s. So you've got this, and it's very clear that you can see that the ice expanded and pushed down this far and has since receded. You know, you don't have to be a glaciologist to see that. Well, during the Big Ice Age, of course, these whole valleys were filled with glaciers. So these are the kinds of things that clued scientists into the fact that there had been a Big Ice Age. They were able to study the effects of the Little Ice Age and learn a whole lot. So this has been going on since the mid-1800s. It was not my intention to spend a lot of time on that tonight. But yeah, okay, we'll look at some of these very quickly because you can see the evidence here for yourself. There's a glacier from 1775 to 1780. You see how it's come down out of the valley and is encroaching upon this village. And here as it was in 1966. The glacier is way up here. This is a photograph. This is probably a woodcut. But what you can clearly see is the difference between, say, 1780 and 1966 is that the glacier has receded. And now it's way up here. And all of this down here is moraine that's now got forest growing on it. See, so all of this occurred with the recession of the Little Ice Age between, say, the mid-1800s. This was like a century of recession. So if you recall, if you read the climate change studies that look at anthropogenic warming, basically they're like post-World War II. Prior to World War II, we weren't pumping enough CO2 into the atmosphere to do diddly squat. Here you see, these are in the Alps, and here you see the glacier again encroaching upon villages. There were, in fact, whole villages that had to be abandoned during the Little Ice Age. And here is a photograph as it appeared in 1966, and see there's no glacier there anymore. But what you have right here is woods growing on the moraine that the glacier left behind. You see here, when they took the photograph, they tried to take it from the same perspective as this woodcut here. In this one, you see the glacier coming down. In this one, the glacier has receded far up valley. Same glacier from another perspective, and you can see how enormous it was and how it really did. When you go back and begin to read the accounts of this time, it really instilled a deep sense of foreboding into the people that were watching these massive glaciers just coming on, sometimes 100, a couple hundred feet a year, coming on, just encroaching upon, and then, having to disrupt, their complete life. Now there it is in 1966. There's the glacier up there. Here, all of this pile here is a pile of moraine material, but you can see the obvious difference. In 1966, the glacier had receded all the way up here. So bear in mind that when somebody starts showing you pictures of glaciers receding, and they go, look at how it looked in 1970 and look at how it looks now, you know that what you're seeing is the last phase of a process that's been going on for 150 years, 3/4 of which had already transpired before humans had a discernible effect on the climate. Okay, the Franz Josef Glacier in the southern Alps of New Zealand. And this, I picked New Zealand because it really does show the global extent of the Little Ice Age. Look at that big rock right there that is clearly in this drawing or painting is covered with glacial ice. And just to give you a sense of scale, that's about a kilometer right there, 3/5 of a mile. Okay, so here's that same rock. This is in 1905, and you can see it's uncovered all of this stuff in front that was buried in 1872. So here's 1905, and here's in 1940. Now it's receded up valley, and this area down in front here is a lake. Right down in front here, that's the lake that you see. There's where the lake forms. So that's where the lake is. So you can see that the glacier has diminished in size quite significantly. Yeah, here's another one, growing out onto the valley floor during the Little Ice Age. Big Ice Age, this is the way it is now. So this graphically portrays how dramatically different. Now, if you want to talk about this and put this in terms of traditional concepts, we would say this is the winter of the great year, and this is the summer of the great year. Same concept, just using different terminology.
Did that much weight up there, did that affect anything on the Earth itself?
Yes.
The tilt of the...
Sam, you have forgotten the lecture I gave on Atlantis. What detail did I give during the lecture on Atlantis that relates to the question you just asked? How many of you guys remember isostacy?
Oh yes, that word.
Yeah, it squeezes.
Thank you, Paul. Thank you.
The asthenosphere, and it causes all kinds of lines and places like that's effect.
Yeah, very good, very good. This is along the shore of Hudson Bay, and what you see here are shorelines. It'll be clear what you're seeing right here. See, up here is present sea level, and what has happened is this was where the ice was 2 miles thick. And with the unloading of the ice, with the loading of the ice, the crust of the earth under it was squished down thousands of feet. With the unloading, the crust has been coming back. Now the crustal rebound is a delayed response. The ice melted away faster than the crust rebounded, and that's why you've got these elevated shorelines. But if you went back through the course of the Holocene, this is like a record of the 10,000-year uplift since the glaciers were removed. And yeah, so you had these kinds of changes. Now what I have maintained is most of the polar shift theorists are not taking isostatic adjustments into account. And I think that here we have a mechanism for provoking pole shifts, because you remember the Earth is an oblate spheroid, and the distance of the surface of the Earth from its center of gravity is dependent upon its latitude, right? Well, if you change by thousands of feet, like see, this is that thing I was talking about earlier, the North American craton, what you're looking at right here. This is that big granitic core of the North American continent. And that thing has just been pushed down by a couple of thousand feet. Okay, now it's rebounding. As it's rebounding, it's moving away from Earth's center of mass. Okay, this is going to that's going to induce forces that are going to cause an attempt for the Earth's crust to reach a new equilibrium. However, if you suddenly move something several thousand feet further away, what's it going to have to do, Jerry, to compensate? It's going to have to move to a different latitude.
But wouldn't the same thing have to shift when it sinks down too?
Don't go away.
Okay.
You saying this is 1,000 feet higher than it used to be?
Yes, when it was under the ice.
And it's coming apart? As it goes up, is it?
It's rising up.
All right, and so the circumference is getting bigger. Well, tell us what the lines are.
The lines, okay, no. Charles is asking, what are these lines here? The lines are beaches. See, here's Hudson Bay. The water, the Earth's ocean level stays more or less constant. Now, the land rises. So you've got a beach right there. Now the land rises 10 feet, 50 feet, and that beach gets isolated.
Is it sand dunes?
There's probably sand on it, yes. But I haven't been.
Is it frozen?
I would also guess most of the year it's frozen.
They call it tundra?
Yeah, mostly tundra around Hudson Bay.
Frozen beaches, tundras.
Well, I'm not sure if but it's beaches. And I would say that most of the year, yes, it is frozen. It may be.
Salivating on that sand.
I know, he's.
1,000 feet, it's 1,000 feet from the level of the water to the highest one of these beaches.
At least. Now, I don't know about in this photograph, it may not be 1,000 feet because that's not necessarily the highest beach. But you see right there, that's a very prominent beach. So undoubtedly, for a period of time, the crust stabilized at that level. The ocean etched a fairly prominent shoreline, and then the uplift continued, which now isolated this shoreline above the ocean.
There's 5 shorelines in Georgia. The Fall Line, the Hazelhurst, the Okanogan.
Yes, but now there's a difference there, Charles. Those beaches are the result of the ocean going up and down. These beaches are the result of the land rising. So you've got, this is called isostacy. The ocean level rising and falling is eustatic changes as opposed to isostatic changes. Yes.
So you say when it goes upward, when it goes back up, it's going to change it's going to shift the axis, but wouldn't it shift also when it goes down? Because that's also another swoosh.
Sure.
So it would shift going down and going up.
Because bear in mind, when something is going down, to compensate it, something else needs to be rising. When you have the onset of an ice age, you have several billion, trillion tons of ice accumulating over the land mass. The land mass begins to compress down into the mantle by thousands of feet. Meanwhile, you've got the plastic asthenosphere material that gets pushed to the side. Now, if you go away from the center of the glaciers, of the squish, you're going to come to a place, picture that you've got a big beach ball. It's sitting here with no pressure on it. Now you come and put your thumb and you start pushing down on the top of it, the sides are going to bulge, right? Think of that as isostatic change. As that glacier presses down, parts of the earth are going to rise to compensate so that the total of the earth's crust maintains the same average distance when averaged for every coordinate point on earth. You see, that's how the earth is maintaining its equilibrium. So that means that as that crust was going down, somewhere else crust had to be rising. And that's why I believe Atlantis will eventually rise again. The problem is, though, when it rises again, we'll be going into an ice age, and that will not be a yay at all.
They worried when they flooded Kiowa, Hartwell, Russell, Johassee, Truman, all those lakes over on the Savannah River. They worried about all that water was going to compress the earth.
Right. Because even that small amount of water can cause a discernible compression. Yes, it can. Oh, you can go out where Lake Bonneville was, out in the Basin and Range province of Utah. If you follow those shorelines from Lake Bonneville, they're not horizontal anymore. They're tilted. And they've risen more. In fact, what was originally a level, where the lake was deepest, has risen the most. So if you follow the shorelines now, they do this. You follow them up and then down. And where they reach their greatest elevation, that's where Lake Bonneville was the deepest. So yeah, the crust of the earth is a malleable material. And the onset of glaciers, an ice age, and the termination of an ice age can cause major changes. That's why the deglaciation was accompanied by some of the most spastic volcanism of the last 50,000 years. There were enormous volcanic eruptions throughout the whole deglaciation process 10 to 12,000 years ago. Massive ones. And that was undoubtedly the result of this redistribution of surface mass, which then triggers all of these secondary consequences down in the magma zones, and creates pressures. So now you have the upwelling of huge amounts of magma and volcanic eruptions. You had huge volcanic eruptions in New Zealand. You had them in the Caribbean. You had them up along the Cascades. Yeah, there were a lot of very large volcanic eruptions occurring. That's why some of those flood layers have sandwiched between them these thick layers of volcanic ash, which I've give you a sample of sometime.
Go back to that picture of Hudson.
Oh, I closed that.
I know you did.
Sorry.
But referring back to yeah, are those dunes, are those shorelines all the way north and south, or did you just happen to find one spot?
Well, they're more prominent in some places than others, but they're all around.
East side.
That's on the west side. The pictures that I showed you is on the west side of Hudson Bay.
But it looked like there was land on either side of the shores.
Well, it may have just been a little, the Hudson, there may have been a bay. It was probably a bay within the bay that we were looking at. I've actually found that place on a map, and I don't really remember specifically. It was up there by, if you're looking at Hudson Bay, it was like roughly like at 8 o'clock.
But you don't picture it's going from all the way from the south to the north, the shoreline like that.
No, because, well, the uplift is going to be differential. The uplift is greatest where the ice was thickest. Over Hudson Bay, it was 2 miles thick. And then as you get out towards the perimeter of the ice sheet, you're looking at something that's 2,000 or 3,000 feet thick or 1,000 feet thick. And that's why the uplift, has been the greatest, because the depression was greatest where the ice was thickest and heaviest. So when you've removed it, the uplift is greatest under those zones. And so when there have been maps made, Charles, of the isostatic lines radiating out from the center of the ice sheet. And you can see as you move towards the perimeter, the uplift has been less. Although, for example, out the west coast of Canada, along British Columbia, north of Seattle, what happened there was as the ice pushed down, the perimeter lifted up by hundreds of feet. So when the ice was removed, it's almost like you can picture, if you push down on something and there's an uplift around the rim, that's what happened. So as the ice was removed, that dropped back down. And that uplift, that was related to a lot of the Cascade volcanic eruptions that occurred. Mount St. Helens blew its stack a couple of times, big time, around 11,000 to 13,000 years ago, and left its signature ash layer in the flood layers. Okay, so what we've been talking about here is the general idea that in order to understand Earth change, we have to expand our thinking to include the cosmic domain on all fronts. And that is the major paradigm shift that I conceive has to occur in the human species within the next generation in order for us to have a future on this planet. We're cosmic beings seated on this planet, and our destiny is cosmic, and we're now in the transition zone where we can begin to see that cosmic forces have played the dominant role in our own history on this planet, as well as the history of life itself. I have selected this particular episode as being one of several extremely important events that have happened in recent history that serve to clue us in to the bigger events. In the same way that we can understand the big ice age, the great winter of the world, by looking at the little ice age, we can understand the great ekpyrosis that the Greeks talked about by looking at these more modern firestorm events. I've taught you two terms. Cataclysmos was the Greek term for the destruction of the world by water. Ekpyrosis was the Greek term for the destruction of the world by fire. We've spent a lot of time in here looking scientifically now, the scientific evidence of how the world has been destroyed by water through cosmic floods. We've spent some time looking now at cosmic fires. When we go back to October 8, 1871, we find a microcosmic analog for the ekpyrosis of the ancient Greeks, or the apocalyptic fires of the book of Revelations, or all the other traditions. We can look here at, very briefly, looking at some of these that I've collected from various sources, which are always being interpreted by the scientific community as being purely allegorical or metaphorical or metaphysical or psychological, if they have any scientific validity at all. They're not looked upon as historical. Therein is a great mistake. When we turn to these traditional sources, I think we have to look at them as history. This is what I have written here. Ancient myths and religious prophecies are replete with tales of world destruction and catastrophe resulting from all-consuming fires. Analogous with ancient tales of universal destruction from a great deluge, only a few survivors remain in the aftermath to replenish the race. The ancient Greeks told such tales and referred to the process of world destruction through fire as ekpyrosis, the counterpart to cataclysmos, or world destruction by flood. The biblical account relates that the world was previously destroyed through the agency of water and will suffer destruction through fire at some unspecified future date, which is euphemistically referred to as Judgment Day. As with the flood story, the vision of a world-destroying fiery holocaust was by no means limited to the Greeks or to the Bible, but is found in dozens, if not hundreds, of traditions from all over the world. The Mayan codices, direct quote right out of the codices, at the close of the ages it hath been decreed, the world shall be purged with a ravening fire. From the Mahabharata, the Indian tradition, at the end of the Yuga, when men become fierce and destitute of virtue, then does the Yuga come to an end. And the course of the winds will be confused and agitated, and innumerable, very important detail right here, innumerable meteors will flash through the sky foreboding evil. And then the sun will appear with 6 others of the same kind. And all around will be din and uproar, and everywhere there will be conflagrations. Fires will blaze up on all sides when the end of the Yuga comes. Now, if you read your Vedic traditions, you discover that the great cycles, the Yugas, the Kalpas, and so on, are directly tied in with this series of cosmic events. They're giving us direct information here that needs to be interpreted scientifically. The sun will appear with 6 others of the same kind. Does that mean that 6 other suns are going to suddenly appear in the sky? No, not stars, but something which from our perspective may provide a source of light as bright or as intense as our own sun.
Could be a reference to the age.
Well, and there could possibly be. I will not claim that I have the final word on any of this. From traditions of Brazil, talking about their god of fire, Monan, without beginning or end, author of all that is, seeing the ingratitude of men and their contempt for him who had made them thus joyous, withdrew from them and sent upon them Tata, the divine fire, which burned all that there was on the surface of the earth. The Hopis talk about when it rained fire on the earth and the people took refuge underground. The Norse traditions talk about, from the Voluspa, or the Eddas, the elder Eddas, Surt from the south comes with flickering flame, the sun darkens, earth in ocean sinks. Isn't that what we were just talking about? Fall from heaven the bright stars. Fire's breath assails the all-nourishing tree. Towering fire plays against heaven itself. Now see, once we begin to appreciate and recognize that these ancient traditions are actually very precise, scientifically encoded knowledge, we will be able to advance at a whole new rate, because we have ignored these traditions thinking that they were the outgrowth of a superstitious, pre-literate, unscientific mind. That's not what they are. They're as precise in their symbolism as modern science is. And when modern science begins to recognize that, we will begin to be able to look at those and begin to decode these ancient traditions in a new light.